In this problem 1b, you have 5 different configurations here, but you don't actually have to find out any numbers really, you just have to know the order of the configurations in terms of the potential energy here. Now since there are four different particles for each one, you're actually going to be having 6 different forces of attraction here, which means 6 different potential energies to calculate for each one. All the charges of these are the same, so the only difference for this is going to be the radius, which will determine the strength, the magnitude of it, and also whether they're repelling or attracting will determine the sign of the energy here. So what I did here is I just represented K times Q1 times Q2 as capital Q just to make it easier. You don't know the values for any of these, but you know that they're constant in all of the potential energies here, so you can just represent that as like a unit. And then for the R, you could just represent the lateral distance as like 1 unit, and then in reference to that, since it's a triangle with both lengths, it's a right triangle with both of the side lengths being 1. The diagonal length is going to be √2, which means that the R is going to be equal to √2. So you divide it by √2 when it's a diagonal force or a diagonal potential, whatever. So then for each of these, you're going to basically add up the different energy the different potential energies. So for the first one, you can see this here on the lateral side of things, you got 2 potential energies where they're attracting and 2 where they're repelling. And then also in both cases of the diagonals, they are attracting. And I represented the K, Q1, or Q2 as just capital Q here. And then the lateral ones, they're being divided by a radius of 1, so it's just the Q itself. And in the diagonals, they're being divided by √2, as you can see. So that's Q plus Q minus Q minus Q minus Q √2 twice. And that gets you, I did change that here. But that's just going to get you negative 2 over √2Q. Then for the second one, all 4 are positive. So it's going to be like that, but like number 1, but all 6 potential energies here are going to be positive since they're all positive. So then that's going to be Q plus Q plus Q plus Q plus Q over √2 plus Q over √2, which is going to be ended up being equal to 5 plus √2, as you can see here. Then for number 3, it's you'll see that you have half of the lateral forces are attracting and the other half are repelling, and the same goes for the diagonal, the 2 diagonal potential energies, and so that's all going to equate to 0 because they all cancel out. And if you go down to 5 and skip 4 for a second, you'll find that it's exactly the same. Despite the fact that 3 and 5 are different, it's just the reverse, and that has no effect on the potential energy, it ends up being the exact same thing. And then for problem 4, you'll see that on the lateral side, there's all 4 lateral potential energies are negative, so that's negative 4q, but both of the diagonals are positive, which equates to negative 4 plus root 2, which is like approximately negative 2.6 or something. And so now you basically have the values of all of the potential energies for all 5 configurations. Now you don't have actual numbers, but you're able to relate it because you don't know what K, Q1, or Q, well, you know what K is, you don't know what the charges are, so you can't calculate the actual energy value, but you can just represent that with a Q, so it's good enough for like just being able to rank the configurations. And as you can see, number 4 is the lowest because that's the greatest negative, and then would be number 1, and then number 3 and 5, which are both 0, and then the greatest potential energy is 2, which is the only one that has overall positive potential energy, which is interesting how that works. It's like they gotta all be the same to have positive potential energy in the system. But that's the answer.